Good evening, everyone. Thank you for joining for today's live session for the NPTEL course Computational Mathematics using SageMath. As is the custom in each of these sessions, we'll be going through a few examples together, and which should help us understand the concepts taught in the course better. So, some of the examples I have today have been chosen from the practice examples itself. So, let us begin. The first example, it asks us to use the ODE integration module or ODE function from SciPy library to solve an initial value ODE. So the ODE that we are given is y double dash plus 3y dash plus 2y equal sine of 2x with the initial condition y of 0 being 0 and y dash of 0 being 0. Once we solve this, we are also asked to plot the solution curve. So before we go into the solution itself, I'll just like to share my notebook. Okay, is this visible? Uh, okay. Okay, so here I'm looking at the same problem that we have been asked to solve using Python, which is y double dash plus 3y dash plus 2y equals sine of 2x. And these are the initial conditions that have been provided. So as you can see, this is an ordinary differential equation. So if I want to classify this is an ordinary differential equation of second order because you have the term d square y by dx square coming here, and also the right hand side of this is uh, not homogeneous. So I should write this as heterogeneous second order ODE with initial conditions that are provided. In mathematics, the way we solve this is like, if some of you have gone through like the basic the engineering mathematics, say as part of your curriculum, then you would know that the standard way to solve this problem is to first try to solve the homogeneous part of the equation, which looks like y double dash plus 3y dash plus 2y equal to 0, and for that obtain a homogeneous solution which is of the form yh of x. And the second part is to find a particular solution which exactly satisfies the given ODE. So the particular solution should exactly satisfy the given ODE. And with a little bit of sorry, with a little bit of prior knowledge, you can understand that a solution should be of the form of, say, a sine of a cos of 2x plus b sine of 2x. Once you put down all the once you assume this as your particular solution yp of x, you then evaluate all your first and second derivatives and plug this into your uh, ODE, given ODE, and then we separate the terms with coefficients of sine of x and cos of 2x because uh, they they will vary independently and both of them will not be zero at the same point. So like you do not have a point where sine and cos both simultaneously go to zero. So if we look at these equations and rearrange them, we essentially end up with two equations for the two coefficients capital A and capital B, giving us a particular solution of the form yp of x equals minus 3 by 20 times cos x plus minus 1 by 20 times sine of 2x. My general solution is then written as sum of my particular and homogeneous part of the solutions, from which in which now I substitute my initial conditions y of 0 is 0 and y dash of 0 is 0. Together, this gives me helps me evaluate the coefficients for the homogeneous part of the solution. So these coefficients are phi and beta. Once they have been evaluated, I get an overall solution which fits my. So this satisfies my ODE plus initial condition. Right. So this is how analytical approach to the problem would look like. And as you can see, there are like a lot of steps here. Easily we have written like around 25-30 lines, and that too I have taken some shortcuts. So if you want to solve the same problem in Python, but remember that this is no longer a first order ODE for which we have used our ODE int function, ODE integration function in Python. The way we would rewrite this is we rewrite a second order ODE as rewrite second order ODE as two first order ODEs. So how do we do this? And they should be linked. So I I write a vector v of x which includes my terms y of x and dy by dx. Then when I take the first derivative of my vector dv by dx, this underscore denoting the vector, I end up with the vector which is dy by dx and d square y by dx square. I just write this in the shorthand notation. So this is y dash and this is y dash y double dash. From our OD we know that, sorry, no, this is from our OD we know that y double dash equals sine of 2x minus 2y minus 3y dash. Both y and y dash are components of vector v. So therefore we can write v dash to be equal to y dash sine of 2x minus 2y minus 3y dash, which is nothing but the first component, the second component of the vector, and sine of 2x minus twice of first component of a vector minus thrice of second component of vector. So something, I'm writing this in the zero index notation, which is how we, which is what we use in the Python code. So what I want to stress here is we have gone from a single ODE, which is a second order ODE, and now replaced it with two first order ODEs. And then my initial condition becomes at x equal to 0, y of x equals y dash of x equals 0, which means that at x equal to 0, my initial condition is vector v is 0, 0. Right, so this is the basics behind it. Now we'll go back to the code and implement this there. So on the code front, we'll first start by doing our necessary inputs, which are numpy, OD integration function from scipy integrate, and matplotlib.pyplot. Then I'll run this function called as help of OD integrate so as to see how we'll use it. This is like a simple step in between. I'm just calling it because here in the one of the examples, right, sometimes you might find useful things. So here in the example itself, they are trying to solve a second order ODE of the form theta double dash plus b theta dash plus c sine of theta equal to 0. And then they are doing the same thing whereby they are rearranging their variable to be y equaling theta and omega being first derivative of theta. And then calculating dy by dt as omega and uh, the second term coming from our second order ODE. Once they do that, they'll go ahead and find the solution using ODE where they'll substitute this function pend, which is essentially first derivative of the vector y, give y0 initial condition as shown here, and then t is the entire solution space, so 0 to 10. And any arguments for the function can also be provided here. And this is how they proceed to solve this. So we'll do it in the similar step. We first define a second order function called as ODE second order, whose input is which takes input parameters as vector and x. Then the vector, as I mentioned in the notes, we rewrite it as the two components y and dy by dx. First derivative of the vector will become first derivative of y and second derivative of y respectively. So those can be plugged in either through the vector itself or through the uh, provided ODE. And then we return the first derivative of this vector. Next step is to initialize what solution space do we want. So suppose I want solution for x between 0 to 10 and over 100 with 101 uh, with 101 points in total including 0 and 10. So that's like 100 equal parts of the 0 to 10 space. So each part will have the width of 0.01, sorry, 0.1. Next, we initialize give the initial value of the vector, which is initial value of y of 0 and dy by dx at 0. So those both being 0 from our problem, our initial vector weight 0 is also 0, 0. Now we move to the solution part. Our overall solution vector written in capital is obtained by using ODE int with second order ODE as my derivative function, ODE second order as my derivative function, x0 as my initial condition, x as my entire array, solutions array. And if I run this if I run this only till this point and say print vec, what do I get? So each of the point of vec at each vec is basically y of x and dy by dx, y and dy by dx at some provided x. So the first term being at x equal to 0, the next term being at x equal to 0.1, all the way till x equal to 10. So I'm now just splitting the vector into y and dy by dx respectively. So I get uh, two arrays, one y and the other one be dy by dx, both in capital. Now I'm plotting them simply using matplotlib, and if I put grid legends and show, what do I get? I get two plots, first one being y of x, the second one being y dash of x. So you can see that the blue one is our solution curve and it has some sort of periodic nature to it, but its amplitude seems to be going down slowly. The second derivative also has some curve associated, also has a period associated with it, but its amplitude doesn't seem to be seems to be on the rise. If I want to play around with the solution space, say suppose I want to find out for a very large value, what do I see? You can see that our solution clearly has a periodic behavior and there is some sort of sharp decrease and then after that it's almost constant. Okay, so I'll go back to our original values. Right, and just to see if what we are getting is correct, I also tried to solve this using the analytical method, which I detailed, whose steps I detailed earlier. So if you can remember, our solution had something into cos of 2x plus something into sine of 2x plus something into e raised to plus a constant into e raised to minus 2x and another constant into e raised to minus x. So I define this as my analytical solution function. And now what I do is I do a scatter plot for the solution that we have obtained using Python and do a line plot for the solution that we have obtained using our analytical methods, so analytical solution of x. If I run this, what do I see? can see a like a perfect match between whatever solution we expect from Python and whatever solution we calculate if we were to do a hand calculation. So, which tells us that this ODE integration function is pretty reliable. There are a lot more parameters here that you can play around with. So, there are like these extra parameters which contain how much should the tolerance of the solver be, what should be our attempted step size, minimum and maximum of those step sizes, and so on. So these can be played around if suppose whatever we are trying to solve, we do not get the solution straight away, but it's a pretty decent solver. As you can see, like a very complicated function also has been solved within seconds by Python. Okay, is this example clear? If not, you can say raise your hand or paste your doubts in the chat. Okay, okay. I presume this example is clear. As there aren't
Yes,
any
yes, sir.
doubts. Uh, okay, thank you. We'll move on to the next example. So here we are being asked to use the curve fit function in SciPy and try to fit a curve of the type ax square plus bx plus c to the set of given to the set of points given below. So I have already included the points here directly in the code itself. Okay, we'll first start by doing the necessary inputs, which are again your numpy, matplotlib, pyplot, and curve fit from scipy.optimize. The points that we are given, that we have been given, are shown here. So like points are written in the form of x comma y, xi comma yi, and for all the points. So you can see we have a total of 11 points here. X increasing in steps of 1, going from -5 to +5, and y is what we are observing. We estimate that or rather we expect, we hypothesize that our curve will follow quadratic, this will follow quadratic curve, so we want to see how it works. But before that, let's do a quick look into the uh, curve fit function. So as you can see, curve fit takes like a number of inputs, but the most important ones are and which are required are your function f, which has information about what sort of function that we want to curve fit, your x data and your y data. This should be like your sequence of observed data, and there are a lot of other points your such as bounds, sigma, and all that. Once it returns also a few things, and as it can say that it also has a few errors that it can raise. Suppose if your x and y data contains nans, or if for whatever number of your iterations your least square minimization fails, things like that. And how do we use it? It also mentions which reference is used, so those of you who are interested could look at something like this. And how is the function used? We first define our function with the parameters required, which are, say, here they are trying to define a function a into e raised to minus bx plus c, where a, b, c are the parameters. And then they try to obtain the fitting parameters and covariance matrix using curve fit applied to the function with x and y data being fed as its inputs. Then you could say plot it and see how it is. It also mentions that our function should not be over parameterized. So what does this mean is you could theoretically write a function which has say 10 polynomial terms rather than a quadratic term, and then see how sorry and then see how uh, it could in theory give you even better result than say your quadratic term. But if the number of parameters are very large, then you also require a data set that is sufficiently large so as to arrive at a unique solution which or the best solution for provided parameters and function form. So we'll first start off by quickly looking at how our function actually looks like. So these are the given points. We plotted the code is pretty straightforward. As you can see, we are obtaining x and y data and then plotting a scatter plot with the label given points. We are also showing a grid, and the legend basically turns on this label for the data. So you can see our curve seems to follow a trend like this, which is why say a line may not be a suitable option. We have chosen quadratic function to be our option, quadratic function to be our choice of function form which we want to fit our data to. So we define our quadratic function based on input x with parameters a, b, and c. So whenever we define such a function, right, function f here in the here also I think they should have mentioned that whenever we define this function f, right, the first argument is always your independent variable, and the remaining are taken as fitting parameters. So you cannot write say f of a b c comma x, right? So x must be the first parameter, first argument to the fitting function. That is how it's written by default. And our function we have taken to be of the form ax squared plus bx plus c. Suppose I write now I run this. Next I try to fit the curve. So we have params in covariance as a covariance matrix as our output from the curve fit function, which takes quadratic function x data and y data. If I just do this, I get some parameters and a covariance matrix. The smaller these values are, the better. And you can see that these three params correspond to the last three uh, last three parameters apart from the first one, which is present in the quadratic function. So we have now obtained some fitting parameters, and now we want to plot both the original data against the fitted data. So how do we do this? We again obtain our x data and y data. Sorry. Oh, okay. Is everyone comfortable with Hindi? I can do that. Is everyone comfortable with Hindi? Someone
Yes,
raise
sir.
their hand for Hindi. Okay. Okay. I'll try to do both in brief because I think part of this video has to be uploaded on to YouTube for the wider audience. So I'm unsure if Hindi would work through, but I'll do this once in Hindi also. I'll just finish this explanation for the English part, and then would that be all right? Okay, good. Thank you. Uh, so, uh, so right, we are now plotting our fitted curve against our original data. Again, the x and y data is obtained from our points itself. we do a scatter plot for xy data with given points, and uh, then for the fitted curve, what do? Is we use NP linspace to create, say, like 100 points, and 101 points I'm doing here, and this creates my X array between the first and the last value of X data, so which is -5 to 5, and then I'm feeding that X array into my quadratic function. And if you remember from the last class where we had studied star args, we are passing all our arguments together as a list. So params is already a list. We are passing this list directly, and what this tells my quadratic function is this first thing is my X array, and then ABC have to be taken one after other from the params list. So A will be 1.6, B will be -2.8, and so on. So, and if I run this now, what do I see? I get a function which roughly fits our given points. Okay, uh, I'll give a quick explanation in Hindi as well. Okay, do you guys want me to start from the beginning for this problem, or any particular point that was unclear, which I should explain in Hindi? Okay, let's go from the beginning itself. So, uh, हमें बेसिकली इस प्रश्न में ये पूछा गया है कि हमें कुछ पॉइंट्स दिए हैं x, y, जो यूज करके हमें एक कर्व फिट करना है, क्वाड्रेटिक इक्वेशन का कर्व फिट करना है, y इज इक्वल टू ए एक्स स्क्वायर प्लस बी एक्स प्लस सी। और इसमें हमें ये निकालना है कि ए, बी और सी क्या, इन पैरामीटर्स का क्या वैल्यू ऑप्टिमम है, क्या वैल्यू बेस्ट है इन पॉइंट्स को रिप्रेजेंट करने के लिए। हमने इस हफ्ते में क्लासेस में ऑलरेडी ये पढ़ा है कि इस चीज के लिए हम या फिर ऐसे काम के लिए हम लोग कर्व फिट यूज कर सकते हैं फंक्शन, जो कि scipy डॉट ऑप्टिमाइज में मौजूद है। हमने जब कर्व फिट का हेल्प देखा तो हमें ये पता चला कि कर्व फिट में तीन सबसे महत्वपूर्ण इनपुट्स रहते हैं। एक हमारा फंक्शन है, एक हमारा एक्स डेटा, और तीसरा हमारा वाई डेटा। ये छोड़ के भी काफी सारे आर्ग्यूमेंट्स है जो हम इस कर्व फिट फंक्शन को दे सकते हैं। और इन्होंने जैसे लिखा है यहाँ पे कि हम ये मानते हैं कि वाई डेटा इक्वल्स एफ टाइम्स एक्स डेटा विथ हमारे फिटेड पैरामीटर्स प्लस सम एरर गिवन बाय एप्सिलॉन। जब हम फंक्शन एफ लिखेंगे कर्व फिट यूज करने के लिए, तो ये महत्वपूर्ण है कि पहला आर्ग्यूमेंट इस फंक्शन का हमारा इंडिपेंडेंट वेरिएबल रहे, जो कि एक्स डेटा है, और बाकी के उसके बाद लाइन से जो भी पैरामीटर्स एक या दो या चार जो भी रहेंगे वो हमारे फिटिंग पैरामीटर्स माने जाएंगे। जब कर्व फिट इस फंक्शन एफ को देखेगा तो वो सोचेगा कि पहला वाला इंडिपेंडेंट है, बाकी जितने भी है लाइन से वो सारे फिटिंग, वो सारे पैरामीटर्स क्या वैल्यू निकालने का है, वो फिट करने का है। फिर एक्स और वाई दोनों अरे होने चाहिए। ये जानने के लिए कि कौन से टाइप का फंक्शन बेहतरीन रहेगा, तो हमने सबसे पहले हमारा डेटा प्लॉट किया एक्स कॉमा वाई, स्कैटर प्लॉट किया रादर देन लाइन प्लॉट, जिससे हमें अंदाजा है कि इंडिविजुअल पॉइंट्स पे डेटा कैसे दिख रहा है। ये देख के भी हम एक अंदाज लगा सकते हैं कि इसमें जैसे कि एक लीनियर लाइन फिट अच्छा नहीं करेगा, बट शायद क्वाड्रेटिक फंक्शन थोड़ा अच्छा फिट हो जाए। तो इसलिए हमने क्वाड्रेटिक फंक्शन लिखा जिसमें पहला इनपुट है x, जो हमारा इंडिपेंडेंट, पहला आर्ग्यूमेंट है x जो कि हमारा इंडिपेंडेंट वेरिएबल है, और a, b और c ये हमारे पैरामीटर्स है जो कर्व फिट हमें निकाल के बताएगा। फिर कर्व फिट कैसे यूज करते हैं? कर्व फिट में फंक्शन डालना f ऑफ x, फिर x और y, और उससे दो आउटपुट आते हैं, एक हमारे फिटेड पैरामीटर्स और एक कोवेरियंस मैट्रिक्स। फिटेड पैरामीटर्स हमें बताते हैं लाइन से कि कौन से वैल्यू और कौन से वैल्यू हमारे पैरामीटर्स ने लेने से हमारा ये जो क्वाड्रेटिक फंक्शन है वो बेस्ट रिप्रेजेंट करता है ये वाई डेटा को। अभी यही एक्सरसाइज करने के बाद हमने बेसिकली सेम चीज की है कि हमने गिवन पॉइंट्स को प्लॉट किया है और हमारे फिटेड फंक्शन को प्लॉट किया है। तो फिटेड फंक्शन जो कि क्वाड्रेटिक है और जिसका पैरामीटर आ रहा है कर्व फिट फंक्शन से, वो करने के बाद हम देख सकते हैं आंखों से ही कि मतलब फिट काफी डिसेंट आ रहा है। अभी एज एन एग्जांपल समझो मैं इसको चेंज कर दूं, समझो सिर्फ लीनियर कर दूं, या फिर मैं एक दूसरा फंक्शन लिखता हूँ क्वाड्रेटिक टू एक्स ए बी। अगर मैं इसको बोलता हूँ कि मुझे एक लाइन ही फिट करना है ए एक्स प्लस बी फॉर्म का, तो अगेन हमें तो अंदाज है ऑलरेडी कि अच्छा फिट नहीं आना चाहिए, बट हम फिर भी एक बार कोशिश करते हैं। तो इससे ऐसे कुछ आ रहा है, और अगर मैं इसको इसमें रन करूं तो कैसा दिखेगा, तो मेरा लाइन कुछ ऐसा आ रहा है। आप देख सकते हैं क्लियरली कि ये लाइन ट्रेंड लाइन को फॉलो नहीं कर रहा है, मतलब उससे बाहर निकल के कुछ अजीब दिख रहा है। ओके, to those in English, I'll repeat the last part. Suppose we are adamant that we want a linear fit to this given data. While we can see from the scatter plot that doesn't seem to be a good idea, we proceed with it anyways with a function of the form ax plus b. And then when we find out the parameters and covariance matrix, we use the parameters to fit to our linear data. And we can see that the output linear line that we are getting poorly represents the given points. So perhaps after all, quadratic was a good choice. Okay, तो both in English and Hindi में भी जो सुन रहे हैं सबको clear है? Is everyone clear what happened in this problem? Anyone has any doubts? Okay.
Yes.
Oh, okay. Thank you. Okay, I'll do the same thing again because I have to also give an explanation in English also. So I'll do the same steps again. First in English, then in Hindi. If you have at any point any doubts, you can just stop me there. Okay. The third problem, the third example, asks us to find two zeros for a function which is given with the form f of x equal to e raised to minus x by 2 minus x times sine of x. And it asks us to do the same using both bisection method as well as Newton-Raphson method. So how do we do this? We first again begin by our same thing. We import matplotlib.pyplot numpy, and from within SciPy optimize itself we get bisect and Newton. So uh, in the previous example we obtained curve fit, which was also from SciPy optimize, but ODE int was from a different submodule. You can check it here also. It was from SciPy integrate. Okay, so SciPy has a lot of functions which you could say, which you could explore also yourself, apart from whatever we go through in the classes. Some of you, especially those who will deal with say signal analysis or wave propagation, might require Fourier transform or fast Fourier transform. FFT is inbuilt into SciPy itself. Similarly, linear algebra modules are also there. Okay, so the next step is to define a function f of x which basically returns e raised to minus x by 2 minus x into sine of x. So this is my function. Now I want to plot this function for a given domain. So 0 to 10 and with 100 points is my x array, my y array is func of x. Directly I can feed this numpy array and it will calculate for each of the points in the numpy array. Then I will plot this using a line plot, and I'll also plot a grid. This is important because I want to see where the curve cuts the line y equals 0. So once I do this, what do I see? This is my line y equal to 0, and I can see that it cuts at a point between 0 and 2. There is a route between 0 and 2. There is uh, another route between say 2 and 4. A third route can be found between 6 and 8. Another route can be found between 8 and 10. So these are the four places for the chosen domain. It's going from 0 to 10, where our function is cutting the line y equal to 0. So we know that whatever we have chosen, we now have four routes in this domain. So let's start with bisection method first. Again, as I have done previously, I'll first look through the help document. I see that the bisect function takes three arguments are minimum required. First is the function f. Next you have a and b, and what do we say? It's a basic bisection routine to find root of the function f between the arguments a and b. It requires that f and a and f of b do not have the same sign. And what is mentioned here is it's slow but sure. So we have discussed in the last live session also a bit about bisection method. There we had written down our own code for the bisection method, and we had also commented on this part that if there is a root between a and b, bisection will get you that. So how do we go about it? Your f is required to be a Python function which must be continuous with f of a and f of b having opposite sides. A and b are basically the two ends of your bracketing interval. There are other optional parameters such as relative tolerance, maximum iterations, and so on. And to use it, it's very straightforward. We optimize bisect f between a and b. So if I want to solve my uh, obtain my roots, I know one root lies between 0 and 3, 0 and 2. I know another root lies between 2 and 4. You can see this from the graph again. There is a root around say somewhere around 0.9, and there is another root say somewhere around 3.1. So I expect my bisect function to get me these two roots, and then I'm printing it directly. Okay, so you can see that this happened very quickly. We obtained two roots as 0.8592 and another root as 3.071. So these are the two roots that we obtained using bisection method. Uh, another Another method that we have been asked to use is the Newton-Raphson method. So again, I will look into the help document. I see that there are two required arguments, first being the function, second being x0, which is my starting or the initial estimate of the root. And if my function is not scalar but vector, then appropriate form of x0 should be provided with it. The third term is f prime equal to none. So f prime, when f prime is given, when f prime is not given, the method will this Newton function will default to a second method where first derivative is not available, and it tries to estimate first derivative numerically. The other ways, if you have the first derivative you supplied and the Newton-Raphson, then your Newton function basically becomes your Newton-Raphson method. And here is something interesting, that the convergence rate of Newton-Raphson is quadratic, so it's much faster than your bisection method. Okay, but it suffers from a problem where if the initial guess is say too far away from the root, then you may not get a solution at all. So a very large number of iterations might be done, you still not get it. And how do we use it? To use the second method, we initialize our function f, give our initial estimate. Whereas if we want to use the Newton-Raphson method, we provide f prime, we provide f, we provide our initial guess, and we also provide f dash or f prime. Okay, so since we are interested in using the Newton-Raphson method, we'll define our f prime, which if you obtain the first derivative is nothing but minus 0.5 e raised to minus 0.5 x minus sine of x minus x cos of x. Then I proceed to solve the Newton-Raphson method. I know one root is around 0.85, another root is around 3. So I take two values close to those roots, and I also provide my first derivative. And then I calculate my roots. You can see that these two roots 0.859 and 3.07 exactly match with the roots that we have obtained from bisection method. Okay, hope this is clear. I will quickly go through this in Hindi again. Okay, so इस प्रश्न में हमें पूछा गया है कि एक फंक्शन है f of x जिसका जो लिखा जा सकता है e raised to minus x by 2 minus x into sin of x, और इसके हमें दो जीरोस या दो रूट्स निकालने हैं यूजिंग दो डिफरेंट मेथड्स, पहले बाइसेक्शन मेथड और फिर बाद में न्यूटन-रैफसन मेथड का प्रयोग करना है। तो सबसे पहले जब हम इंपोर्ट करते हैं तो हम बाइसेक्ट और न्यूटन ये फंक्शंस इंपोर्ट करेंगे scipy डॉट ऑप्टिमाइज में से। उसके बाद हम एक बार हमारा फंक्शन का उसके बाद हम हमारा फंक्शन f of x डिफाइन करेंगे विच इज e raised to minus x by 2 minus x into sin of x। ये डिफाइन होने के बाद हम हमारा फंक्शन का प्लॉट निकालेंगे y is equal to f of x करके। सो y equals f of x ये है और इसका प्लॉट निकाल रहा है। हम प्लॉट निकालने पे देख पाते हैं कि जिस पॉइंट पे y इक्वल टू 0 ये लाइन क्रॉस हो रहा है, ये ग्रिड लाइन क्रॉस हो रहा है, वो हमारे रूट्स है और हम देख पाते हैं कि रूट्स 0 और 2, 2 और 4, 6 और 8 और 6 to 8 और 8 और 10 इन इंटरवल्स के बीच में मिलता है। उसके बाद हमने बाइसेक्शन मेथड पे हेल्प देखा समझने के लिए कि कैसे बाइसेक्शन मेथड यूज करना है और क्या उसके आर्ग्यूमेंट्स देने हैं। सबसे पहला आर्ग्यूमेंट f है और उसके बाद के दो आर्ग्यूमेंट्स, उसके बाद के दो रिक्वायर्ड आर्ग्यूमेंट्स है हमारे जो एंड्स ऑफ द फंक्शन है a और b। यहाँ पे ये जरूरी है कि a और b ऐसे रहे सो दैट f of a और f of b दोनों साइमल्टेनियसली पॉजिटिव या दोनों साइमल्टेनियसली नेगेटिव नहीं होने चाहिए, दोनों में से एक पॉजिटिव एक नेगेटिव होना चाहिए जो कि 0 और 2 पे वैलिड है। अगर यही मैं समझो चेंज कर लूं 0 और 0.5 इंटरवल पे, तो प्लॉटिंग से भी हमें दिख ही रहा है कि प्लॉटिंग से ही हमें दिख रहा है कि वो नहीं वहां पे रूट नहीं रहेगा या फिर एक रूट नहीं रहेगा। एक और केस हो सकता है जैसे कि समझो आप एक पॉइंट दे रहे हो 2.5 और दूसरा पॉइंट दे रहे हो 7, तो 2.5 और 7 अगर मैं इंटरवल देता हूं तो दोनों वैल्यूज निगेटिव है। इसका ये मतलब नहीं कि दोनों को बीच में रूट नहीं है, आप देख सकते हो कि दो रूट है। तो अगर साइंस हमारे अपोजिट रहे तो हम गारंटी कर सकते हैं कि मिनिमम एक रूट है। अगर साइंस सेम रहे तो 0 या 2 या 4 रूट्स हो सकते हैं। इसके लिए ये इंपॉर्टेंट है कि हमारा फंक्शन f of x कंटिन्यूअस है जो भी हमने डोमेन x चूज किया है। अब ये इसके बाद हम बेसिकली हमारा बाइसेक्शन फंक्शन रन कर रहे हैं जिसमें हम फंक्शन दे रहे हैं और इसके इंटरवल दे रहे हैं। तो जब हम ये रन कर रहे हैं इन इंटरवल के लिए तो हमें आंसर मिल जा रहा है जो मैं बोल रहा था। अगर वैसे चेंज करूं मैं, हमें पता है कि 2.5 और 7 के बीच में दो रूट्स है, तो हमारा एक वैल्यू एरर आता है जो कि बोलता है कि f of a एंड f of b का साइन डिफरेंट होना चाहिए। सो इसलिए सही इंटरवल देना जरूरी है। फिर उसके बाद हमने न्यूटन मेथड देखा जिसमें इनपुट फंक्शन है, इनिशियल गेस है, और फर्स्ट डेरिवेटिव फंक्शन उसके बाद देना है। तो वही हमने फिर डिफाइन किया है नीचे, फर्स्ट डेरिवेटिव फंक्शन डी फंक ऑफ एक्स। सिंपली एनालिटिकली आप df बाई dx कर सकते हो, उससे ये आ जाएगा एक्सप्रेशन। उसके बाद हम रूट्स, दोनों रूट्स निकाल रहे हैं अराउंड द पॉइंट्स विथ इनिशियल गेसेस 0.5 एंड 2.5। हम एक्सपेक्ट करते हैं इससे सॉल्यूशन आएगा और बाइसेक्शन के सॉल्यूशन के साथ मैच होगा। दोनों चीजें हमें सही से दिख रही है दोनों रूट्स के केस में। सो ये था कैसे इस्तेमाल किया जाए बाइसेक्शन मेथड और न्यूटन रैप्सन मेथड। ओके, अभी कोई डाउट नहीं होगा तो हम आगे बढ़ते हैं। किस चीज के लिए? अच्छा, हेल्प। ओके, how do we get help? So help is already inbuilt in Python. So suppose you have help of help is already inbuilt in Python. ये जो help हम लिख रहे हैं ना, you do not need to import it from somewhere. It is already inbuilt. And if I do this, sorry, uh, uh, just a second. हमने we have already imported numpy as np. So help is like जैसे plus minus and all these operators are inbuilt, right? Help is not exactly an operator, but it is also inbuilt in Python. And what it does is it gets the function description. So all these things that you are seeing with help, right? They are actually inbuilt in the function itself. Suppose, for example, I want to write a description here. So I'll do this some uh, returns first derivative of f of x defined above, input x float, and I'll say that this is my value where the first derivative is to be implemented. Suppose I write a description inside the function. So I'm writing a description inside the function by using this three uh, three, what are these called, inverted commas, double inverted commas. So if I write this sort of description between two of these things, right? So this is what my help function will return. So suppose I do now help on defunct. Defunct is my, defunct is my function. So it will tell you what does it. It prints out whatever we have written in the description string. This is what we have written. So similarly, when you do a help of Newton, right? All those people who have built this SciPy module, right? They have already put a description inside those functions, which makes it easy for us to understand, interpret, and then use the functions accordingly. So as a good practice, say in research or even in jobs later on, also it's a good idea to write your own function descriptions in brief, where you tell about what is your input, what is your output, a brief description of what the function does, and an example of how do you run this function or use this function. Okay, this help command is is inbuilt, so you don't need to import it from somewhere. Hope this helps with the question. Okay, I suppose this help is clear now. Uh, okay, if there are no more questions, I will move to the next example. Okay, consider that you have a nth degree polynomial which is of the form p of x equals a n x raised to n plus a n minus 1 x raised to a n minus 1 all the way till a1x plus a0. And since this is an nth degree polynomial, we expect it to have n roots. The roots may be real or complex, the roots may be repeated or distinct, but it will have n roots in total, which we represent by alpha 1 to alpha n. And then we want to see, then we know analytically that there are a few relations like this, which needs to be satisfied. So, summation of your roots or summation of product of your roots provided the square of a root is not included, summation of like a triple product of the roots. Okay, so we want to see these properties, we want to see them we want to verify them with our own example. So an example that we are choosing is a polynomial with degree 6, and we are going to use the function numpy dot roots to find the roots of this polynomial. Okay, so let's start with the imports. Only numpy is required here, and we write our own coefficients for a 6 degree polynomial. So these are chosen randomly. You could also say a float somewhere, right? Something like this you could have. And if this is my now polynomial, next I look at the help on numpy.roots function. So it says that roots takes a single argument p, where p is what is p? P is an array which contains rank 1 array. So it's basically like a 1D array which contains all the polynomial coefficients. How is it used? Suppose you have coefficients as 3.221. So this represents the equation p of x equaling 3.2 x square plus 2x plus 1. And now we are asked to calculate its roots. That is done using np.roots score. So we do the same thing. We have defined our coefficient array, and we are obtaining the roots, and then we are printing it here. We expect 6 roots. So you can see there are 6 roots. You can also see that 4 of these roots have 0.j. So 4 of these roots are indeed real, whereas 2 roots are complex conjugates of each other. Now we move on to the first property. The LHS of the first property is simply sum of your roots. So we have sum of our roots, and RHS is minus an minus 1 by an, which in our case is minus a5 by a6. Note that our coefficients array contains the largest coefficient of the highest degree first. So this means that our equation reads 2x raised to 6 minus 3.2 x raised to 5 minus 5x raised to 4 plus 7.x cube all the way to plus 2. So when I do this LHS and RHS, this coefficient of 1 is nothing but a5 and coefficient of 0 is a6. Sum of roots. Let's see what do we get. Okay, the first for the first property, LHS is 1.6 plus 0j, which is nothing but 1.6. RHS is also 1.6 ratio of the coefficient. So the first property is indeed satisfied. We look at the second property. So the second property asks us to calculate alpha I into alpha j, sum of alpha I into alpha j, provided that j is less or equal to I. J is less than I. So that is what we are doing by restricting j. We are taking I for all the roots, for all the roots. So all 6 of this, whereas j is being restricted to uh, j is being restricted. So I suppose I have the third root, then I only multiply this with the first and second root. That is how I do it. This is to avoid any duplicate multiplication that may arise, as well as any squaring terms for each root. And then I also write my RHS, and once I run this, you can see that my LHS is minus 2.5 and my RHS is also minus 2.5. Finally, the third property, again the same thing, alpha I, alpha j, alpha k with I greater this I greater than j greater than k. With this in mind, I run over, I add all the triple multiplications and check it with the ratio of coefficients. Okay, you can see that everything is spick and span. All the three properties are satisfied properly. Okay, so I hope this question is clear. Uh, I could go through this in Hindi also. Is anyone requiring a Hindi explanation here? Okay, I guess not. Uh,
No, sir.
no, right? I think whoever wanted is not here. Okay, yeah, so this completes the fourth example. Okay, the fifth is we want to create a Python class named sphere with radius as an input, and it should have two methods to print volume and surface area. So how do we do this? We create the class sphere. Uh, Within it, we import our numpy, and then we initialize it with the radius r. So self.r is equals r. The string, the double underscore string double underscore function, which is what we obtain when we do a print of a sphere object, will return something of the form sphere with radius self.r. Percentage if acts as a placeholder for a floating point number. Next, you have the method for a volume, and you also have a method for surface area. So the volume is 4 by 3 pi r cube, and the surface area is 4 pi r square. Right. So this is what we have here. Then I run this class. I initialize a sphere of say radius 5 and assign that. So SPH basically becomes a sphere object of radius, sorry, an object belonging to sphere class with radius 5. What would happen if I give nothing? It will say that one positional argument was missed. And then when I do next thing, what I'll do is print sphere. So that this should call the function. This is same as doing sphere dot double underscore string double underscore. So same as this. And then we print the volume of the sphere as well as the surface area of the sphere up to 4 decimal points, up to 4 digits past the decimal point. So you can see that this is what we get. Sphere with radius 5, volume is given here, and surface area is given here. Okay, the next example that we have is where we are asked to. Okay, this problem is clear, right? I think it's pretty straightforward, but if you have any doubts, you can stop me now. Okay, I think it's clear only. Next example, the sixth example, we are right. we are asked to write an account class to represent a bank account created with an account number and a starting balance. We want to include two methods, which are deposit a certain amount and withdraw a certain amount. It's important that withdrawals be only done if sufficient balance is present, and once we also want to include a print function. Sorry, we also want to include a function where we print out the account information, specifically the account number and the balance. So how do we do this? We define a class account. It is created using account number and starting balance. So you have account number and current balance here as being fed into the initialization double underscore init double underscore function, and we are assigning an attribute called as account number with the value given as the account number, and another attribute called as current balance uh, to this account object, which equals whatever balance we have inputted. Next, we are defining a double underscore string double underscore this string function. This is required when we print an account object. So what does this string contain? It contains an account number. Percentage s acts as a placeholder for a string object. So here we are feeding the self, the attribute called as account number, self dot account number. In the next line, we are also printing current balance, and here we have percentage f, which acts as a placeholder for floating point numbers. There we are asking it to place the current balance attribute for this particular account object. Okay, if we only have say these two methods, and I look at what my account looks like. So my account one looks like say some account number I've taken 3526 with a balance of say 1300, 1500. Doesn't. If I now run this, oh, I have not run the class account. So if I now run this, something is has occurred here. If I now print this, I get account number as 3256, current balance being 1500 rupees. If I do print the type of this account number, right, it's saying that it's a the object ACC1 is an belongs to the class account. If I look at its attributes, account dot account number, they are 3256, which is a string you can see here, and account dot current balance, which is 1500. Okay, so far so good. Next, we want to add two functions, deposit and withdraw methods. So the deposit method contains everything will have the argument self itself, but it also includes another additional unnecessary argument amount. What we are doing here is to the attribute current balance, we are adding whatever deposit amount comes, whatever is the deposit amount. So our current balance increases post this deposit function, and okay, right. Here we could actually add one more thing. Amount is greater than 0. So we are ensuring that our deposit adds to the account current balance. Cannot add negative deposit amount. Okay, so simple thing here, but anyways, this is what we have. Next function that we have is the withdraw function. Again, it has two. It again has self and a necessary argument in the form of withdraw amount. Again, you could do this if else thing here also. But more important thing is that we'll assume that our amount is our current balance. If it is lesser than our amount, right? So this is the check that we have to include. Then obviously you cannot withdraw, right? Otherwise, your current balance has to stay non-negative. So this condition violates that. So this is what we have added in the. This is why we have added an if-else condition. If it's lesser than whatever amount we are withdrawing, then just subtract it from the current balance. So suppose to my account one, ACC one, I am now depositing 120 rupees. What do I get? So nothing has happened. I mean, the method is executed, but we do not see what has happened, which is why I am printing this account. So now you can see that account number 3256 has an increased current balance of 1620 rupees. If I wish to withdraw, say 1700 rupees out of this, we expect this withdrawal to fail, and that is what we see, that we have that an error has arrived here, which tells us that our withdrawal amount exceeds our current balance, so withdrawal cannot proceed ahead. If I now want to say print the current status of account 1, it should be unchanged, right? So this is unchanged from here. Next, I withdraw a smaller amount which can be withdrawn, and if I now print my account, I see my current balance has decreased. Alright, so a very straightforward example. The point here is that classes like this, right, like your sphere or account, so these are very customizable. Suppose you are working with a bank, or suppose you are working in a bank or have a bank as a client, it might be helpful for you to actually create classes like this with some methods inbuilt that could uh, help to deal with account objects easily. So that is a sort of the power that comes up in uh, the power that comes up with object-oriented programming languages. Can create customized objects. As an example, so like part of my research, I also create some specific uh, nodes which basically represent different form of composites and whatever their attributes are, say stiffness or their uh, electrical resistance, stuff like that. So these can be done very easily with Python, where you create a class which suits your needs. Okay. The next example that we have is we want to create a Python class with the name rationals and want to include those special methods that professor discussed in the class for addition, subtraction, multiplication, and division. So any rational number we know is basically a numerator divided by denominator. So we create a rational the using two terms, numerator and denominator, as inputs, and assign those two as my attributes. Once that is done, I have this string function which is useful for printing, and you can see that I'm now writing an F string. So this is what we have done in a lot of print examples, and I'm telling it to output something as numerator divided by denominator. Okay, so if I run, say, like this, A is rational 6 by 2, B is rational 1 by 4. If I ask it to now print A, I get 6 by 2 as the output. If I ask it to print B, I get 1 by 4 as the output. Right, so this is how my rational numbers look like. Next, I want to add these two together or subtract or multiply them. So how do I do this? Here is an important point. This double underscore at the end and at the beginning, at the end, make this a private method. So how do we? So suppose if I do not include this math from math import GCD here, right? And instead, they said, and I basically need to place this method, uh, this import inside my addition function. So if I place this here, and if I were to remove this from the addition function, right, it won't work. But before that, we'll look at how our addition works. So we are adding two fractions of the form a by b plus c by d, which is nothing but a into d plus b into c divided by b into d. So this is what basically my sum numerator and sum denominator look like. Next up, we calculate the GCD of a numerator and denominator so as to reduce them to the smallest fraction possible. And then I divide my numerator and denominator sums by this GCD and return output as a rationals number, as an object of the rationals class with some numerator and some denominator. So if I run this, again I go through this process. If I now do print a plus b, right, you can see that it's saying here that the name GCD is not defined. So GCD is not defined for this function, even though we have imported it here. So it's a private method. So I do this here now, and if I now run this, say 6 by 2 plus 1 by 4, which is 13 by 4. Right. Similarly, I have written a subtract method which does a by b minus c by d. Again, you get it as ad minus bc upon bd. Again, calculate their GCDs, subtract them, sorry, divide by GCDs, and then return a rationals. So, were I to do a print of a minus b, I get 11 by 4. Next, I have the mul method, which does for the multiplication. A by b into c by d is nothing but ac upon bd. Again, divided by GCD and so on. So there are a lot more methods. I think start somewhere here. There are a lot more methods you can see, right? So this special methods, you have your init, you have your call, string, representation, then you have for addition, subtraction, multiplication, division, your powers, less than, greater than, less or equal to, greater than, equal to, equality, non-equality, and so on and so forth. So you could use any of these and add them to our rationals class here. Okay. Uh, Hopefully this is clear. If not, you could raise your hands. Okay. Next thing is the example 8. So here we have a we are asked to create a class called as country, which should store the name of the country, population, and its area. Right. Then we want to write a program that reads a set of countries and prints the countries with largest area, country with largest population, and country with largest population density. So we'll first look at the class country. As mentioned, it is initialized using the country name, population, and attribute. So we specify uh, three attributes as name, population, and area, and assign them to our input values of name, population, and area. Next, in the string function or the print function, we want to print what is the country name. In the next line, we want to print its population. In the third line, we want to print its area. So that is how we are doing. We are doing this using an F string, and you can see that this is pretty straightforward. The third thing is we are including a method called as get population density. So once this function is called, we create an additional attribute called as self.population density, and that is nothing but self.population upon self.area. And once this function is called, we want to return self.population density. Alright, so this is how this looks like. I've chosen a list of countries already, so the values that you are seeing here are roughly correspond to have been taken from Wikipedia, but uh, have been shortened a bit so that, or rather approximated a bit. Sorry. So this is what basically a list of countries that I have. So I have 6 objects of the country class A, B, C, D, E, F, and for each object I'm specifying it as country of name, population, area in square kilometers. So I've got 6 countries here: Monaco, Singapore, Netherlands, India, China, Russia, something like this. I run this block, and now I want to see what is the object A belonging to class country. So it's a country called, it's the country Monaco with a population of around 37,000 and area around 2 square kilometers. If I print D, we should get India with a population of 1.42 or around 1.43 billion with a area of around 3.3 square 3.3 million square kilometers. Next, I am defining this list of countries, and now I want to look at the function max area. So this function calculates maximum country with the maximum area among the list of countries. So we it's defined very, like, it's very straightforward. You have, I think you have done something like this before also, but we initialize maximum area to be 0, and we initialize maximum area country to be a blank string. Then for all the country in list of countries, when the area of country exceeds max area, you simply add, you simply replace the max area country with country name and max area with country area. So once this whole thing is done, we want to print country with maximum area and specify what area it is. So if I call this function max area of countries, what do I get? I get the output as the country with maximum area is Russia, and it's around 17 million square kilometers. Same thing I do for a function with population, where I have a list of countries. I specify the, sorry, I initialize 2 variables, max population and max population country, and for all countries in the list of countries, I do the same check as I had done earlier for area, but except now I'm doing it for population of a country. And again, I print a statement out of it, which looks something like this. So the country with maximum population is India. And the third thing is we have a population. We also wish to consider obtain the country with maximum population density. How do we do that? Have our we again have our different countries, but before we but now what we are doing is we are invoking this method country dot get population density. So this method get population density is invoked. What it does is it creates another attribute population density to the object of class country, and then that is what is being compared, and we find the max of that. And once that is done, we print out whatever the value of maximum population density is and the country. So it's Monaco with a population density of around 18,500 people per square kilometer. So this is how it looks like. All right. So with this notebook, I have covered like the first 2 parts being classes as well as users of SciPy and SymPy. Now I have a smaller. I also have a small set of problems for SageMath, which was introduced. I'll share that screen now. So none of all of these are pretty clear, right? No questions here, I suppose. Okay, we'll go to the SageMath. Okay, so you can see here that on the top right corner, it's saying SageMath 9.3. No one had any issues with installing SageMath, right? I think for especially for Windows, the procedure was very straightforward. I believe that everyone was able to install it properly since there are no complaints there. Okay, we are in the first example, we are asked to calculate LCM and GCD of two numbers A and B and verify this simple identity that the product of LCM and GCD of two numbers equals the product of the numbers themselves. So I've written A and B to be 10 and 15 respectively. And if I now look at the type of A, as we have seen in the class, it's sage.rings.integer.integer. So this is the class that we have uh, chosen, class that we have active once we provide it with once we provide SageMath with an integer. If we take the LCM of A and B, it's 30, 3 times A and 2 times B, and the GCD should be 5. But if I multiply A and B and compare with LCM and GCD, we get the same values. If I move it around a bit, suppose I say 85 and he has 115, what do I get? Again, LCM is pretty large, GCD is large, but the identity holds true. So this identity is pretty fundamental. So I believe that most of you have should have come across this identity in the grade school, and it's very elementary to prove this also. So, all right. Now we have in the class we had looked at a concept called as XGCD, uh, which basically gives us the GCD between two numbers A and B, and also finds out coefficients x comma y such that x into A plus y into B equals my GCD D. So if I go back to that, suppose I write x GCD of 15 comma 10. So what does this expression tells us? The GCDs of these two numbers is 5. If I do say 18 comma 10, the GCD of these two numbers is 2, and it is equal to minus 1 times 18 plus 2 times 10. So which is minus 18 plus 20, again 2. So XGCD is an inbuilt function in SageMath that we have used. And now what I'm doing is I'm trying to solve this for, suppose I have three numbers of the form 15, 18 and 35, right? And now I want to find a way to obtain the obtain the integers PQR. All right. So how have I done this? I'll shift to the notebook once. Right. So we are interested in trying to solve a question of the form. We want to solve a question of the form. Given integers a, b, and c, and PA plus QB plus RC equals D, with D being the GCD of A, B, and C. Right, so this is what we want to do. So how do we do that? We first go to our like the first part of the GCD. So we use the identity, or we use the relation that there exists m comma n such that ma plus nb mn belonging to integers ma plus nb equals g, with g is equal to gcd of a comma b, right? So we use this, and we also use the fact that gcd of a comma b comma c is nothing but gcd of a comma b comma c. So the greatest common divisor for A, B, and C, all three of them, has to be same as the GCD of C and whatever GCD comes out of A and B. So if I use the equation that I have written above, and what we get is G is equal to GCD of A comma B, then MA plus NB equals G. So this is my first statement. Next statement is D is equal to GCD of ABC, but which is same as GCD of A comma B comma C is same as GCD of G comma C. So from this D equals, from this we can write X, or I think I use a different notation. Uh, X, I use X only, X into G plus Y into C equals D. These are the two relations that we have. If we use the first relation and input it here, what do we get? X times MA plus NB plus YC equals D. So you have X into M into A plus X into N into B plus Y into C being D. Now we know that X and X, Y, M, N are all integers. Therefore, XM, XN are also integers. With this in mind, we can rewrite X into M as P, X into N as Q, Y as R. From this and this, what do we get is PA plus QB plus RC equals P. So this is the expression that we want. So we now have a method to evaluate P, Q, and R as well as D, provided integers A, B, and C. Okay, going back to our SageMath notebook, this is exactly what I have done. Is in the first part, I am calculating GCD between A and B, which is, as I have written in the expression, this is G, this is M, this is N. And in the next part, I have written this to be D, X and Y, and my PQR are X into M, X into N, and my GCD is D itself. Right, so if I run this, what do I get? It's taking a bit of a time. Oh, okay, I made a mistake. It's GCD of AB is nothing but P. Right, so this is what we have, and if I run this, So is this equation verified? So minus 1 into 15 plus 1 into 18 is 0 into 3. This is, yeah. If I change this a bit, say 12, 18, 33, I get 5 into 12, which is 60, minus 5 into 18, which is 90. So 60 minus 90 minus 30 plus 33. Again, I end up with 3 itself. Okay, so uh, I think this should be clear. PA plus QB plus RC equals T. Okay, if there are any doubts in the logic, you can stop me now. If not, I'll move ahead. The next example is we want to find the factors of sum of the digits of say 1275 factorial. So how do I do that? I write the integer small n equaling 1275. Next, I invoke the method dot factorial. So before we do this, we could actually look at the help document also. As I mentioned, it's you just write help, which is inbuilt, and then write the function, which is n dot factorial. Factorial. This should get me the help on the factorial. Okay, so the help function, it's a factorial function. It's a method of sage rings integer dot integer, which is what we have, and it's used as integer dot factorial self. So you just write integer dot factorial with close brackets, and that is what you get. And it has a problem if with the overflow error as well as value error if the number becomes too large, or if we are trying to obtain the factorial of a negative integer. So I write capital N to be n dot factorial, which is 1275 factorial. If I now print it, you see a very large number of digits here. And if I just take, say, the number of digits, right? So how do we do that? N dot n digits, if you remember. There are 3,408 digits in this factorial. So it's a very, very, very big number. And if I take all the digits of this factorial, that is nothing but n dot digits. This will give me all the digits starting from the units place, ending up to the highest order. So there are a bunch of zeros at the end. Then there may be a few zeros in between, such as this one. I made a mistake. No. There may be few zeros in between also, as you can see here around the mouse cursor, and there are a lot more zeros at the end. So if I do the sum of all these digits and assign it to another integer m, what do I get? M is 13,608. If we take a more palatable example, suppose n is say 5 factorial, say 6 factorial. This should be 750. Let's skip the part. So this, sorry, 720. This is what I get. There are only 3 digits, 0, 2, and 7, and the sum of these digits is nothing but 9. And the factors of 9 are 3 into 3, so 3 square. For the question asked, we just change it to 1275. Again, go through this process. 3,408 digits. The sum is 13,608. Those factors are 2 cube. So 2 cube into 3 raised to 5 into 7. So this is how the factorization looks like. Next, we have another example. Say In this example, we are given an integer d equal to 12 and we are asked to find how many integers are there between two integers n equal to 62 and n equal to 672, which are co-prime to d. So how do we do that? We initialize d to be 12, we initialize n and m to be 62 and 672. Next, we initialize an empty list L. This is where we'll be appending all the co-primes. And how do we find all the co-primes? We write a for loop going from n plus 1 to m minus 1. And what we do is we check the GCD of d comma I. So if this GCD turns out to be 1, if the greatest common divisor between a number I and another number d is 1, then those two numbers are co-prime. This gives me a list L. So if I look at my list L, these are the numbers I am obtaining. So 65 and 12 does not have a common factor. 67 and 12 do not have a common factor. 71 and 12 do not have a common factor. 69 and 12 do have a common factor of 3. So that is why it is omitted. Any number, any even number will also automatically be omitted from 12 because d is divisible by 2. So all the even numbers are automatically omitted. So I can see that this is a pretty long list. If I print the length of L, there are around 203 numbers. And then I just write a print statement to round this all up. Uh, okay, so wait, what is the question here? Okay, function string is used to convert a specified value into a string. So you have to create functions and command under 0. So you have to create commands, functions and command, compute the number of trailing zeros in some factor that you may use. Okay, you want to find the number of trailing zeros in a, okay, yeah, I think we can do that. So the way you are suggesting this to do is we use this function str, is it, string function, to convert value into string. Okay, we could do it from like SageMath itself in an alternate way, where suppose I'll look at the example of this example only, right? Now I know what my n digits array looks like, right? And we know that the n digits n dot the array that we obtain from doing n dot digit starts from the unit place, right? So the first time we get a non-zero number, say I think it is 8, those many zeros, trailing zeros we have in our uh, so I write n digits. I could do it this way also. So n digits is this. Uh, digit, or I'll write I digit. My I digit is 0, while I digit equals 0, and my counter is also 0. I want it to count. Okay, well, I digit equals 0, I digit. I am replacing this with n digits of count. So this will take the first value, and if it is 0, then count is equals to, right. So if I do this, and if say now I print count, saying that I have 319 zeros, and if I do an else at the end of this statement, right, I'll say to print I digit. So it's saying that my first non-zero digit is 8. Okay, so this could be one way. The other way, I'll have to check what you are saying. I haven't fully understood this string part. If you could explain this or like say it out loud, what exactly you want me to do here, I could do that as well. So if I change this number to number that you want, and I just comment this out. Okay, so it's a very large number. There are around 4494. To check if this is correct, I'll use a simpler example. Say n equals 6. This should be 6. This should have 720, 3 digits, 2, and count should be. Okay, I'm doubling my counts. I'm adding. I have an additional count somewhere. I think it is. Okay, so the count is stopping. If right, so suppose I change this to what is 8 factorial, right? 40320. This has only one zero. If I change this to say 15 factorial. So 15 factorial should have three zeros. There is 5, there is 10. So 10 contains another 5 and 15 contains one more 5. So it should have three zeros. Yes, three zeros, 13 digits, count is 3. Okay, so I think this could be one of the ways to calculate the number of trailing zeros as well as the first non-zero digit that comes out. Okay, hope this. Hey, you're saying that you have problems calculating factorial of this number, 17985, is it? Have I understood your question correctly? Okay, let's see running it here. Okay, so this run, say factorial of 5. I change what number were you suggesting? 79. Okay, so this has a. Okay, we'll have to check what. So this value error that we have set, right? So this has a. This is related to our factorial function, so we'll have to seek the help on factorial. Nevertheless, for now, you can see that this thing is indeed working in. Okay, I think I forgot sharing. So, yeah, I can see the same thing that you are saying, right? 4300 digits. Yeah, this is when I'm running this in the Python kernel, right? I have not even gone that far actually. We have said something like 17985 there. Okay, I think I got what's happening. One second. what is this? If I'll just check help on this. So I think here it's mentioned somewhere. I think here we have this. If I change this to, I'll try to change this value. Let's see what happens. Suppose I change this to 10,000. Or how much do we have here in 1780, 17985? We have around 68,000 digits. So, okay, let me look at a simpler example. 1798 has how many? 1798. SageMath is telling me that 1798 has around 5,074 digits. So let's try and change this to 5100. If I now, so you can see that the help function tells us the maximum string digits for non-binary integer to string conversion. So I have now set it to 5100, right? Let's see if it works. No, I think it's doing the same error. I think I've made a mistake, I feel. I'm not sure exactly what's happening here. Still saying 4300 digits. Okay, I'll look this up and get you an answer in the next class. At the moment, I'm not sure what exactly is going wrong. Would that be okay? Okay. I think I looked at this problem primarily in SageMath. I should have checked it in Jupyter, in normal Python itself. That would have probably shown up this error. Okay, let's see. For now, we'll leave that be, and I'll get you the answer in the next class. Sure. Okay. I think we're almost out of time. I'll quickly go through these two questions. So first is we want to find a number of primes between. We want to find a number n such that the number of primes between 2 and n is 10,000. So how do we do this? Our starting number is 2 and it already counts, it's already a prime, so my count is initialized to 1. And till the point my count is less than 10,000, I ask it to find the next prime. And reassign that to my start variable and increase my count variable by 1. If I do this while loop, what do I get? I get that there are 10,000 primes between 2 and 104729. A simpler example, we know that there are 25 primes uh, between 2 and 100, 97 being the 25th prime. So you can see that this code does work as expected. Or if we want to check, first four primes are 2, 3, 5, and 7. So if I look at the first four primes, they are 2, 3, 5, 7 between 2 and 7. So this code does what we are expecting it to do. So the 10,000 prime would be 104729. So both boundaries are also prime. The final question for this session is, suppose we have an integer n and we want to find the number of integers k between 1 and n which are co-prime to n. If this number is k, this k is basically the Euler phi function of n denoted by phi of n. And we want to compare this with Euler phi of n. So how do we do this? We initialize our number n, we create an empty list L, and we run a for loop between 1 to n. So numbers 1 to n minus 1 will be assigned to I. I equal to n doesn't make sense because n is divisible with n entirely, and therefore they are not n isn't co-prime with itself, right? So okay, so we do the same thing where we find the GCD of n comma I, and if it equals 1, this means there is no common divisor between n and I, making them co-prime. Then we add it to the list L. If I now print L, what do I get? I get a list of this sort. So all even numbers are automatically uh, even numbers are all automatically excluded. We can see from the prime factorization that 562 basically has the prime factorization 2 into 281. So all even numbers will be ignored, and 281 and its multiples will be ignored. So for 562, there are 281 even numbers, so those are ignored. 281 itself is ignored. 562 also itself is ignored. 281 is ignored and 562 is ignored. So we expect there to be around 79 to 80. Yeah. So we get our Euler phi value from SageMath to be same as from whatever code length of L that we have written. Alright. So I think this concludes the problems that I had for this particular class.